Can you hear me now? Let's see. Okay. It's so weird. It just does this on occasion and starts uh not allowing me to hear. But now I've got my my freshly boiled egg inside of a carton holder. I'm sorry, that made me laugh. I've just never been so bald before, and it makes me it makes me giggle. All right, so I'm glad I've got your volume back. Anybody have any questions before we get started?
Professor, I don't know if you saw my private message, but um,
Gotcha.
I'm Daniela Brandt for attendance purposes. I know I'm not logged in under the account with that name.
Gotcha. For some reason, it is saying that, but that's cool. Good deal.
Yeah,
Thanks
this
for
is
letting me
my
know.
maiden name account. That's why.
Oh, okay, gotcha. No problem. I appreciate you doing that. Yeah, you guys can go ahead and chat me your first and last name as well. I don't know why the sound just went out. It's been working fine without this headset up until this time. So we're going into chapter three now, but I wanted to invite you guys to ask me any questions you might have regarding chapter two or any other stuff. So, does anyone have any questions? All right, looks like we don't necessarily. So I'm going to go ahead on and begin with our vectors. And I want you to think about, like I've tried to tell you guys in physics, is the best thing when you're learning physics, especially if you've never had physics before, is not to look for how different the things are you're learning in physics are from your everyday life, but to try to find things that's in common with your everyday life. So, for instance, I don't want you necessarily thinking about, ooh, these vectors transform according to this transformation rule. They have magnitude and direction, and they obey the laws of an algebra, blah, blah, blah. I don't want you thinking like that because that's really kind of foreign. I want you to think in terms of the things that you do know. So, I will tell you that vector addition is really equivalent, or one way of stating this is that the very special vector, which is called the displacement vector, that is a vector that points from your initial position anywhere in three-dimensional space, or in principle it could be any number of dimensions, but we're dealing with three-dimensional space. So you can imagine a coordinate system existing somewhere in the universe, and then you draw an arrow from the coordinate origin of that coordinate system. So for a coordinate system, just think of this, because in reality, in order for your coordinate system to be proper or easy to use, you need a right-handed coordinate system. So right now I'm holding up my right hand. My index finger is, notice all three are perpendicular to each other mutually. My index finger, this guy, is pointing in the X direction. My middle finger, which I don't want to hold up that way necessarily, that is supposed to be at a 90-degree angle again from my index finger. So that is at 90 degrees, and that points in the direction of the y-axis. So the y-axis points that way, the x-axis points that way. And now that we have those two, notice the z-axis, which is perpendicular to the x-axis and perpendicular to the y-axis. The z-axis points up according to my right thumb. Okay. So as long as you're using your right hand and you get X, Y, Z, then that in that order will automatically be a right-handed coordinate system. There's ways you can work with left-handed coordinate systems. It's just a pain in the butt to do. So I would tell you guys, if you ever have to draw a third dimension on your coordinates system, to make sure it matches that. Okay, so that's your goal. X, Y, Z. One, two, three. One, two, three. X, Y, Z. All mutually perpendicular. Okay, so the good news is in projectile motion, we're pretty much just doing two dimension because it doesn't matter too terribly much. But now that you have this coordinate system, you can imagine it just sitting here in any orientation you want. It doesn't matter where we are. But if the origin is, say, right here, then if you drew a line from here to where I am initially, let's say this point in space here, if I put a vector, if I put an arrow on the end of it this end over here where I am, then that is a vector that points from the coordinate origin to my current location. Okay. If I move from this location, ends up over here, then that same vector will point from the origin to here. And again, the little head of the vector is over here. Okay. The displacement vector then is from that first spot to that second spot. Okay. So if we think of this as sort of the model vector, that's a good thing. What I want you to understand is, like I've told you before, a vector is a special object that has a magnitude and a direction. It has other principles or other properties as well that are necessary, but it turns out if you're just paying attention and doing what I'm showing you here, you really don't need to think about all those other properties. All you really need to know is it has a magnitude and it has a direction. Okay. So when we're talking about arrows pointing from the origin to the first point I'm at, then it turns out that drawing an arrow is a good representation of a vector, because you can treat the magnitude as the length of the vector from the tail all the way up to the head, and you can say the direction is whatever direction the vector is pointing. So literally in 3 dimensions, so that direction. That's a little harder to classify though. What do we mean? Well, I will show you, or you can look up on my YouTube channel, Cartesian coordinates. You can look up polar coordinates. You can look up cylindrical polar coordinates, and you can look up spherical polar coordinates. And all of those are ways you can find particular points in space and thereby specify directions in 3 dimensions. Okay. So what we normally do is we start with an x-axis that would be horizontal and pointing to the right, say, and then a y-axis that would be up and pointing straight up. Then you could make an angle for measured sort of counterclockwise from the positive x-axis up to a line that connects the origin to a point in in two-dimensional space. That would be a dimension or a way of figuring out direction in 2 dimensions. Now, if it was 3 dimensions, instead of just having that little coordinate system with the y-axis and the x-axis like that, you'd also have to have x-axis, y-axis, and z-axis pointing towards me. So you could imagine, for instance, going directly a point below a point in the z direction, which would be back here. But you could take that line from the origin to right below it, measure that angle, measured counterclockwise from the positive x-axis towards the positive y-axis. That would give you a little angle. So that's a direction within the XY plane. And then you could draw an arrow straight from that dot at the end of that first little arrow that points directly under the point in the Z direction. You could draw another arrow from there straight up to this point in the Z direction. And you could actually take from the Z axis that's pointing at me, allow the angle to tilt down to that vector that goes from the origin to the Z point. That would be another way. Again, not something you need to worry too much about right now. I just wanted you to have some physical feeling, some understanding for exactly what we're talking about. So, what our archetypal or our model vector will be is this displacement vector. And when we talk about the displacement vector, I want you to just remember displacement vector points from the initial position to the final position. Okay. And that means that you have to have, at least in terms of doing the work, you normally have to have some coordinate system drawn, and then you have to have a vector that points from the origin of that coordinate to the initial position, and then the displacement vector just goes from the initial position to the final position. Okay. So let me show you this. I'm going to show it to you in 2 dimensions, and just realize the third dimension just adds a little level of complexity that makes it a little more complicated, but not too big of a deal. So let's look in terms of stuff we already know. I am going to, for instance, try to get, uh, we can imagine a little road right here, and then the road comes to a corner, and there's this road here, and it goes that way, and this road here, and it goes that way. And then maybe it comes back this way. There's another block. There's another road right here, let's say. So I want you to have some idea of a like a neighborhood sort of thing or something like that. So I'm drawing these roads and little blocks where houses might be. So let's say your particular house is right here. Okay? And let's say you go out on the front porch of your house and you're standing right there. Okay? Now I can come back and draw a coordinate system. Let's say anywhere I want, I'm going to put the coordinate system right here. I'm going to draw that as my x coordinate. And I'm going to draw this as my y-axis. I really should have said x-axis as opposed to y-axis. And the z-axis would really be the altitude. Okay. So what I could say right now is this vector, which actually I think I'm going to draw in purple. This arrow represents my initial position. So we could use an X for that. That's often what's done. Some books actually use that. But in general, most physics textbooks, when they talk about 2 and 3 dimensions, they call the vector that points to the position as an R vector. So what I would say is this vector is R, and I would specifically put a subscript on it, I, to represent it. So now I'm going to go ahead and show you I'm going to share my iPad screen with you and show you what it is. I had forgot for a little bit, so I apologize. But here we go. Okay. So it should come up any second now. But luckily, you guys are also brilliant that y'all already figured it out, even though I'd completely forgotten to show it to you. So what I have here are these roads, and you can imagine, for instance, probably north is up, and south would be down, and east would be right, and west would be left. So I could put something like that. I could say east, north, south, west, like that, and that's good too. And this coordinate system just happens to be automatically aligned with those east, west, north, south direction because my y-axis is literally in the north direction and the negative y-axis would point in the south direction. My x-axis points in the east direction and my negative x-axis would point in the uh, west direction. So right now I have a vector that points to my initial position, which is on the front porch of my house. So everybody sees the little red box. The little red box is supposed to be my house, and the little red rectangle on the front of the or on the top of the box is supposed to be my front porch. Okay. So if you want to think about what my final position is, you might imagine me taking a walk, let's say, from my front porch to the sidewalk. So what I'm going to do now is I'm going to imagine that we have a sidewalk and we have some grass, obviously. This would be my yard, say. And then, of course, the neighbor's yard would go like this. And I would have a sidewalk that runs right along the lots, something like this. Okay, so those will be my sidewalks. I might even imagine some sidewalks down the side here, like this. And there might even be some other houses over here and here and here. Obviously, there can't be one right there, so I'm going to say that these people have a really big yard. and these people do not, and so on and so forth. All right. So you might imagine me walking from my front porch to a place in on the sidewalk. Now I have another vector that would point to that location, and that vector would be along this dotted line right here. Now, you can't really see it that well, so I'm not really going to draw it in. I'm just wanting you to understand that at each point, I could draw another arrow that points from the origin to where I am at some subsequent time, and each one of those are recognized as position vectors. So there would be another position vector right there at that dot, and I might even say, let me walk to this corner over to here, and now I could say, this is my final position. So if in fact we were looking at my motion from the time that I went on the front porch until the time I got to the corner, then the vector that points to my initial position was r sub I, and the vector that points to my final position is r sub f. Okay, that's just a common thing we do. Now, what I want to do at this point is show you, zooming in, what's going on here. What I really have, and I will use let's use a light blue for this vector. There is a displacement vector right here. That is the first walk I took. Okay. So I walked from the front porch, which is where that little red dot is. I walked from there to that dot right here. And that was my first little walk. And I'll call that vector A. Okay. And then my second walk, I will represent with the same color vector. And that vector is going to be B. Okay. So what I've done is broken up a walk from the front porch to the corner into two steps, which really is very natural. I mean, it's very common for you to walk off your front porch on probably your walkway down to the sidewalk and then follow the sidewalk down to the corner. What I'm telling you is that now that we have that, remember that picture there? Now that we have that, it turns out that when you go to add vectors, adding vectors is just like uh, putting together parts of a trip. Adding vectors is like putting together different legs of a trip. Okay, so A was the north leg, and B was the west leg. And since the two really followed back to back, then it makes perfect sense for them to be touching each other because I did A, and then at the very end of A, meaning the head of the vector, I then did B, which meant me walking to the left. Okay. So what I'm saying now is just like the displacement are the sum of two vectors points from the tail of the first to the head of the second. So what that means is if the first vector is like the one I drew here, let's say this is V1, and then the second vector is V2, then the sum is V1 plus V2, which we call the resultant vector, which I'll call R12. And the reason why I put a subscript on that is I wanted you to understand that's the resultant vector from just walking vector 1 and vector 2. If I walked vectors 1, 2, 3, 4, 5, then I might want to call that resultant 1, 5. Or if I just did 1, 2, 3, I'd call it 1, 3. Okay. So now I can actually take another vector. Let's say that one would be V3. This one will be V4. And let's say this one will be V5. Okay. So if I draw a vector from the initial position to my final position, then I will get the resultant vector. Oops, made it a little bit crooked there. Let's draw it back from this way, see if I can do a little better job there. Now, these are supposed to be straight lines, and I'm attempting to draw them straight, but obviously they don't necessarily turn out to be straight when I'm drawing them in reality. But this will be vector R15 because it was the sum of vectors 1 through 5. So in fact, it equals V1 plus V2 plus V3 plus V4 plus V5. So that's the key idea I want you to see here is that I can add them 1, 2, 3, 4, 5 like I did there, or I can add them 1, 2 like I did. And the way you can add them, at least graphically, is you draw a tail from the tail, or you draw a vector from the tail of the first vector to the head of the last vector. So addition equals draw arrow from tail of first to, oops, to the head of the last vector. So that's really what we did there, and you can see that. Now, here's something interesting that you might not have known, but I could also write V2 first, and then I could write V1. Now notice there, since vectors have magnitude and direction, when you say two vectors are equal, that means their magnitudes have to be equal and their directions have to be equal. If you'll notice, V2, I tried to draw it exactly parallel to V2, to the V2 I already had, and V1, you'll notice I have it supposedly exactly parallel to V1. I also made the new V2 exactly the same length as the old V2, and I tried to make the new V1 exactly the same length as the old V1, right? But notice when I did this, I actually started from the tail of the second vector and went to the head of the first vector. This setup, as drawn, is called head to tail. Okay, so notice the head of vector 1 is at the tail of vector 2 in the first way we drew it, but that's also the case in the second way we drew it, except the head of vector 2 is at the tail of vector 1. The main thing is you've got a head next to a tail. If you had a tail next to a tail, then that would be called tail to tail addition. Okay, in this case, we got head to tail. So it's very important that you understand graphically how to add two vectors. So, or any number of vectors graphically, because in principle, if you draw this vector to scale, if you drew vector v1, which is supposed to represent, say, me walking from my front porch to the sidewalk, okay, and it was me walking due north, so I could say I'm going to draw an x-axis and a y-axis, and I'm going to make my y-axis point due north. I'm going to make my x-axis point due east, and I'm going to start at the origin, which I represent as the front porch, a spot on the front porch, and I draw the vector parallel to the y-axis. And let's say the distance I actually walked on my front yard was in fact 4 meters. So if I decided to make the vector that's parallel and laying on the y-axis, if I made that say 4 squares long, then I've made up a scale of 1 square equals 1 meter. And if I stick to that, then my drawing will come out to be a scale model. Okay. Now, once I got to the sidewalk, I took a left. In other words, I started walking to the west, which is represented by vector B on the original diagram or by vector V2 on the diagram here at the bottom. So in that case, I would draw it exactly parallel to the x-axis, but in the direction of the negative x-axis. And let's say that one was 8 meters. Okay. Well, if I drew it specifically horizontally and parallel to the x-axis, but pointing to the left instead of to the right, and I made it 8 blocks or 8 squares in length, then I'd have again a scale model of my vectors. So I could actually draw a vector that represents the resultant here, which means this guy. So I could draw a vector from this dot to this dot because I went obviously from the tail of the first, which is this guy, to the head of the last, which is this guy. Okay. And this made my resultant vector, which is this one. So if I were to actually do that, let's say I'm doing it now, I'm drawing a scale model of the vector we just had. The two vectors I took were in fact purple. So I'm going to go up 3 squares like that. And I'm going to go ahead and draw my axes just so we're all on the same page. There's my x-axis, which happens to point due east. And here's my y-axis, which happens to point due north. Now what I'm going to do is walk 8 squares down. So there's 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this distance from here to here is 8.00 meters. Okay. So now what I have is a scale drawing of my two vectors. Now I can draw ostensibly with a straight edge, I can draw a vector pointing from the tail of the first to the head of the last. And when I do that, this should come out. fairly correct if I don't screw up anything. Okay, I'm going to try to use my red. There you go. That's my resultant vector right there. And it obviously ends right at the little intersection of those two rectangles there. So now what I can do is I can pull out a protractor. See, I have this protractor and I can measure what that angle is. And in fact, that angle appears to be at 160 degrees. So that's what my protractor reading here, okay? 160 degrees. Now I can also measure the length. Now, what I notice on my paper is that each one of these blocks is half a centimeter by my scale. So the scale I'm using here, I'll write off to the right, 1/2 of a centimeter, and I'll say on iPad is equal to 1.00 meters on Earth. So that's the scale I'm using. Now I'm going to use the centimeter scale that I have right here. I'm going to use that to measure the length of this vector. Now, in this case, this protractor is not very good in terms of a nice scale here. I've only have it marked to the nearest half centimeter, so that's kind of a pain in my butt. But what I have appears to be 4.80. So this distance appears to be 4.80 centimeters. And notice I'm actually committing to that distance, even though I know for a fact my centimeter scale is not that precise, right? But what I've now figured out is that my resultant vector, which again I could call this one V1 and I could call this one V2, then this one R, oops, this one R is equal to V1 plus V2. So what I think is from the scale drawing, R, which equals V1 plus V2, has a length of 4.80 centimeters on iPad times. Now what I'm going to do is 0.5 centimeters on iPad equals 1.00 meters on Earth. So I can now take 4.80 and I'm going to divide it by zero point 0.5 because that's 1/2. And that gives me approximately 9.60 meters on Earth. Now remember, this angle from here to here is just 90 degrees. So what that means is this angle from here to here is 70 degrees. So I'll say from the scale drawing, R, the resultant vector, has a length of 4.80 centimeters, which equals 9.60 centimeters on Earth, and points 70.0 degrees west of north. Now, you don't have to capitalize the cardinal directions east, west, north. I just did that to make them stand out. But that's what I actually figured out was quote unquote my vector. Now, I just did that and I didn't put much pain into making this very, very precise. If we actually did this with a drafting kit, or God forbid, if you actually had access to CAD and you did it with CAD, it would come out exactly perfect. Okay. But I just did it with electronic screen and a pencil, electronic pencil and that sort of thing. And I have a guess as to what it would be. Now, what I'm going to do is use my knowledge of geometry and trigonometry to figure out what the real answer is. Does everybody agree that V1 and V2 have to be perpendicular to each other? Anybody have any complaints about that? Oops. So V1 is perpendicular to V2. Therefore, V1 comma V2 comma R are a Pythagorean triple. And what that means is V1 squared plus V2 squared, since those two are the perpendiculars, okay, they're the legs of a right triangle, then they have to be equal to the length of R squared. So R should equal the square root of V1 squared plus V2 squared, which would be the square root. We said that was going to be 3.00 meters squared, and we said the other one was going to be 8.00 meters, and that's going to be squared. Well, that was really horrible looking. Okay, so now I get R's magnitude is equal to the square root of 9.00 meters squared plus 64.0 meters squared. 64 plus 9 is 73. So I'm going to get square root of that. And oops, my calculator automatically does something stupid. That is, in fact, 8.54. Not nearly as close as I expected to come, but it's not horrible. So that's 8.54 meters is supposed to be the magnitude. We got 9.60 meters, but again, I didn't do too terribly much to make it real precise. I can and consistently do, like when I'm doing this with protractor, graph paper, a sharpened mechanical pencil, and stuff of that sort. I tend to get no more than occasionally like 5% error, 6% error, but usually even under 5%. But now I also got, because it's a vector, I can't just give you the magnitude. I also have to give you the direction. So I need to figure out what is the angle here. This angle right here. So what we have is a 3 and an 8 and this is our angle, say theta. Can you tell me what trig function relates the 3 and the 8? I'm going to make sure I have my chat box open. Looks like somebody's put something in there. Let's see if that's the answer. Yes, very good. Yeah, that is a tangent vector. Remember, what I use or what I tell my class is some old horse came a hopping through our alley. Okay, so this means sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent. Adjacent means touching is one way of thinking about it over hypotenuse. And tangent theta equals opposite over adjacent. Okay. The hypotenuse, by the way, has to be the one that this little arrowhead, which you probably never thought of it as an arrowhead before, but now you can think of it as an arrowhead and it points to the hypotenuse. Okay. So you can use that. That way, you know there's clearly an adjacent side. That's the side touching the angle. There's a hypotenuse, which also touches the angle, and then there is an opposite side, which touches the hypotenuse, but it does not touch the angle. Okay. Some other people, by the way, use so, ka, toa, and that's fine too. Okay. But now that I know the 3 and the 8 are related through tangent, what I can do is I can say tangent theta is equal to opposite over hypotenuse, and the opposite has to be 8, and the hypotenuse has to be 3. Therefore, theta is the tangent inverse, also called the arctan, of 8 divided by 3. And I'm going to make sure I'm in degree mode, and I'm going to say shift tangent parentheses 8 divided by 3 close parentheses, and this gives me 69.444 degrees. Now, I really only had 3 sig figs in the 8 and the 3, and they were somewhat made up anyways. So 69.4, I actually estimated 70 degrees. So what is my error? Since I really was only able to use 2 sig figs, it's probably best to uh, to think about them. So about those two. So let's say percent error of magnitude. So the actual right answer has to be the 9.60. So what I'm going to do is I'm going to take the absolute value because I don't care about the signs of my percent difference or percent error. So I'm going to take the absolute value of uh, what was my answer? 9.60. So actually, I should call that just 9.6 because, um, I only had on this thing, it only was marked to the nearest half centimeter. So I couldn't really make a good result with it. So I'm going to say it's 9.60 meters minus the actual result, which is 8.5 meters. And then I'm going to divide that by the accepted value, which is again the 8.5 meters, and then I'm going to multiply that by 100%. So I'll say 9.6 minus 8.5 divided by 9.6, and that is 12.1%. So it's not horrible. Okay, it's a little bit higher than 10%, and in our labs at school we're supposed to usually keep it right around 10% or lower. So we're in the ballpark of that. Now, if I do percent error for the direction, it would be in this case, the actual right answer is 69.44 degrees minus what I guessed, which was 70.0 degrees, divided by 69.44 degrees times 100%. That's going to give me a negative, so I'm putting absolute value bars on it. So 69.44 divided by, or excuse me, minus 70 divided by 69.44 gives me 0, oops, gives me 0.806%. So less than 1% error on there. Okay. Again, those errors aren't that critical, but what I was trying to show you is how precise you can be even with really no attempt at being precise. So what we've now learned is a way to add vectors graphically, and that's a really big deal. So for instance, when I draw two vectors that are head to tail, like this, you should be able to draw exactly on there what A plus B is. So any of you think you can do that? What you want to do is just draw A and B like I did on your paper or on your notes, and then draw a vector that includes a tail, a whole length, and an arrowhead, and put what you think the resultant of A plus B is. Okay. I'm going to draw it as well. I will draw it in light blue. And hopefully you got the same thing I did. If you did not, that's okay. You just need to correct yourself. So now I'm going to go ahead and draw it. Hopefully everybody's ready. I'm trying to use a straight edge too, so it looks a little better. This is R, which equals A plus B. Okay. Did anybody not get that? Well, let's amp it up a little bit. I'm going to draw A, B, C, and then D. Now I want everyone to draw a vector that represents the resultant of that because I want you to see how easy it is to add, in this case, four vectors. This one's particularly a pain in the butt for me because the way I drew it, it's almost parallel to that first vector. Okay, remember you guys are going to do it too. Oh, I don't know why all of a sudden it started acting like I needed something. Okay, so now I'm going to use my straight edge to try to draw a vector representing the sum of those four. There I go again. Ah, it's more of a pain than it should be, honestly. Okay, so that's the vector R is equal to A plus B plus C plus D. So everybody knows how to add a vector graphically and add more vectors. Anybody not get that right answer? Notice where the arrow is. That's key. Now, the other thing you have to realize is R equals A plus B. It turns out our addition is commutative. And I mean, it's kind of weird to say that, but the main thing is in vectors, when you add two vectors, A plus B, you could also add them B plus A and get the same answer. Okay. So if I tried to do that, what I would do is I would draw B, which notice was about 3 units long and pointed straight up. So there's my B vector. Now my A vector, I'm going to draw this one just for a very important reason. I'm going to draw it just like I did before, but now I'm going to draw it uh, with its tail to on the tail of the B vector. So I noticed my A vector went over 3 and up 2. So that means I'm going to draw my A vector right to here from there. Oops, I went too far. Let's undo that. I missaw it. So I'm going over 3 but up 2. So that is my A vector. Oops. I don't know why I did that. That's not helpful at all. So this is my A vector right there. And we already know what the solution is. We know it's that blue guy. So what I'm going to do is I'm going to take this A vector and slide it right along the B vector so that I can do the same thing there. And that would convert these two vectors. Notice. So that's another piece of terminology. These were head to tail. These two are head to tail. So what I'm trying to do is show you how you can add two vectors tail to tail instead of head to tail. Right now I have them tail to tail, and you might be a little at a loss for words. What we can do is we can draw B right at the end of A, and then that would make it the equivalent of A plus B. Notice A plus B is supposed to equal B plus A, but I could also draw another A on the other side, and it will also confirm the result that I just got from just putting the B there, and that is this right here. So there's my A, there's my B. Notice I've made a parallelogram. This is called completing the parallelogram. Okay, so I've completed the parallelogram, and my job now is to draw the resultant vector. Remember, resultant is a fancy word for the sum. So draw the resultant vector from the common tail to the opposite vertex. So my vector is just going to be, if I may use the right color again. Evidently I cannot. It's just going to make it whatever color I don't want it to be. I don't know what it did there, but it did not do what I wanted. And it did it again. It seems to be going into trying to put text down, and it's trying to make a, I guess, black text or something. So this is my result. R is equal to A plus B. So with that, I've now taught you how to add vectors when they're head to tail. You draw them from the tail of the first to the head of the last. And when they're tail to tail, you complete the parallelogram and you draw from the common tail to the opposite vertex of the parallelogram. Notice that that R looks exactly like the R above. Everybody see that? Now I need to show you some other stuff that vectors do. So vectors have direction and magnitude, and addition is commutative. Okay, so A plus B is equal to B plus A. Okay. It also follows other properties like the associative. And one way you might think of that is you could say A plus parentheses B plus C is equal to A plus B plus C. So that works. However, you can also, well, multiply a vector by a scalar. A scalar is the fancy word for just a number. Okay? So if the scalar is positive, then the vector resulting will be parallel to the original. So, for instance, you could say this is vector A, and then you could say this is vector 2A, and you could say this is vector 1/2 A. Okay? If the scalar is negative, the resulting vector will be 180 degrees from the original. So if, for instance, if this is vector B, then vector negative B would be this guy. And vector negative 0.5B would be that guy. Does that make sense? Anybody have any questions on that? All right, now I'm going to show you subtraction. Now, you might recall this rule from pre-algebra. There, I thought it was kind of stupid, but when you see it now, I can tell you it's very, very valuable. So the rule is this: A minus B. Notice I wrote three equal bars. That means is defined as it's defined to be A plus the additive inverse of B. So in order to in order to subtract B from A, what you're going to do is add them, but instead of adding B, you're going to add the opposite of B. So let's go back to our original vectors. I am going to draw my one vector, which went from here to here. That's going to be A. And then my other vector, which went from, let's see, that one went over. Oh yeah, I drew it a little different. Okay, abandon that. I'm not even going to try to do the same vectors. I'm just going to do some new vectors. Let's say this new vector is this guy, right? So it's supposed to be going to that corner there. So that's B, and I want to know what is A minus B. Okay? So right now I'm asking, how do we compute A minus B when A and B are in head to tail configuration? So I'm just not taking the time to write head to tail there. Make sure y'all understand what I'm talking about here. So I've got A and B in head to tail configuration. So what I'm going to do is I'm going to remember that vectors have magnitude and direction. So in principle, at least with the vectors we're dealing with now, which means basically everything up until the second semester, okay, you can do anything you want to a vector long as you don't change its direction or its length. So I can imagine sliding that vector B down along vector A. So if I do that, what I get is a series of marks like this showing that I did in fact slide the vector along. Now the vector originally went from the bottom left over 3 to the right and up 1. So I'm going to take it from here and go up to here. Whoa, Nelly, not there. To there. So this is my new B vector. Okay. So what I've done is I've sort of pictured B as if it had a little ring on it, and I could just slide it down the A vector as long as I didn't tilt it, which would change its direction, or stretch it or compress it, which would change its magnitude. Long as I didn't do that, I'm good to go. Now, here's the cool part. I first moved it. Now I've got to, let's see, one, slide the second vector. And when I say second, I mean the second in the subtraction. And then two, draw the negative of the second vector. So the vector is B. Obviously, negative B would be this guy. Okay. Now you can see that the vectors are in head to tail configuration, right? So now I have to do is add. And remember, A plus B is the same thing, or A plus negative B is the same thing as negative B plus A. So I'm just going to draw from the tail of one of them to the head of the other. And basically, I'm going to go from the loose tail to the loose head. So lo and behold, this is vector A minus B. So that's how you subtract two vectors if they happen to be tail to tail, or in this case, they happen to be head to tail initially. Okay. Now, let's do in purple in tail to tail config. Okay. Well, in that case, it's not too hard. I'm going to do the same two vectors. That one vector went over 2 and up 3. So I'm going to go over 2 and up 3. So this is going to be my A vector. And now what I'm going to do is my B vector, which was over 3 and up 1. Was it over 3 and up 1, or was it over 4 and up 1? Over 3 and up 1, yes. Oh, I drew it over 3 and up 1 in one case, I think. But anyways, uh, now what I'm going to do is draw B to be just like this. Okay? Now, in this case, I'm trying to compute A minus B, which is defined to be A plus the opposite of B. So 1, since they are tail to tail, just find opposite of second vector in the subtraction. What I mean is the second vector to appear in the subtraction formula. So in A minus B, the second vector is B. So I'm going to go ahead and draw negative B by just putting a head at the tail and putting the tail at the head. And now I have negative B. And you see, in fact, that negative B plus A is just this vector right here. So 2, draw vector from tail of negative B to head of A. Okay. So let's see, for instance, make sure you guys can do this. Let's say we had, whoa, I don't know what happened. I switched to a marker by, or switched to a highlighter by accident. So let's say, dang it, why does it keep doing that? Let's say this is vector A, And let's say this is vector B, and I want you to draw A minus B. So you guys try to figure out what A minus B would be on this one. And I might have drawn it so tight that it's hard to actually get on here. Let's see. Yeah, I might have made it a little too big, so I'm going to erase just a little bit right there and a little bit right there. So imagine that you've got an exact replica of that drawing, and what you want to do is try to write A minus B, just that final vector on this diagram. I'm going to do it, and then you can check your answer with mine. Okay. So this should be a fairly good representation of negative B. Notice I drew negative B right next to B, but then I allowed myself to slide it along vector A. And now I can say A plus the negative of B is that vector. Okay. Anybody not get that? All right. Now I'm going to try one more with A minus B. That one was head to tail, so I'm going to draw, which hopefully y'all have seen this is the easier one. I'm going to draw two that are tail to tail. I'm going to make this one B. I'm going to make this one A. And I want to know A minus B again. You guys go ahead and take a poke at what you think it is. I'm going to go ahead and go about computing it. Evidently, I started recording my something. I don't know why, but anyways. So remember, it's not only important that you get the vector in the right place, but it's important that it's the right length and it points in the right direction. So you got to make sure it comes all the way from the tail, from this point to this point, and you got to make sure that the head is at this end, not at that end. Just like I had to make sure it went to this point, and that the head was at that end and not that end. So everybody got that? Okay. Now it turns out this is all well and good, and you can do everything, but what really is the crux of being able to add vectors is your ability to actually decompose a vector. So I'm going to show you that now. Or decompose R. There's another word for it. R. Uh, decompose R. Dang it, I can't think of the other word. Oh well, no big deal. What I'm going to do is I'm going to draw this vector from here to here, and let's call that vector A. Oh, decompose R, resolve into components. Because it turns out that every vector has, if it's in two dimensions, it's got to have two components, one of which can be zero, that's fine. But the main thing, it has a possibility of two components. If it's in three dimensions, it's got a potential of having three components. And like components can add, but only like components. So in order for you to add vectors, you have to be able to break them down into components. And in order to do that, you have to know what the x and y components are. So I'm going to pretend that I've created an x-axis that points to the right and a y-axis that points up, so that now I can imagine a shadow. Let's pretend like the sun is shining straight down parallel to the negative y-axis, and lo and behold, what we'll get is a shadow right here. Okay, so that vertical light just gave us a shadow right here. That shadow is exactly as wide as the y component of A is long. So this would be called A sub y. And if you're referring to the length, you just say A sub y. But if you're referring to the actual vector, then it's A sub y with a vector symbol on it. This we might call the angle theta. Now, if you imagine a set of laser beams shining from left to right, they would cast a shadow as well, and their shadow would be right here, and that could be a sub. Oop, I said y. Sorry about that, everybody. This is supposed to be x. I don't know what world my brain was in, but anyways, uh, this can be a sub y, or you can refer to the vector itself as a sub y vector. Okay. Now, the rule is AY plus AX has got to equal A. Okay? So that means if you were to walk along one of them from the tail of the red vector towards the head of the same vector, so if we walk along, let's say, from here to here, I walked in the X direction. And now I'm going to walk from the tail of the second to the head of the second. And that should bring me to the head of the vector A. If it doesn't, then I've got them wrong. Okay. But now we can use our fact that the sine of theta is equal to opposite, which would be AY over hypotenuse, which would just be A, and the cosine theta would be AX over the hypotenuse, which would be A. So what we found is A sub X is equal to A cosine theta, and A sub Y is equal to A sine theta. Now, if you always draw the angle pointing up from the positive x-axis counterclockwise, and that's what the angle is if it doesn't specify anything other than degrees, then this formula works as long as you're in the first quadrant. But when you're doing the other quadrants, things get a little more complicated. We'll finish this up next time. I suggest you look at my world's greatest vector addition problem and the vector addition parts 1 through 5. They were in week 2 module. Now they're in week 3 module. They're also obviously videos on my YouTube channel. That's exactly what they are, is links to them. So check them out there. But we'll finish up this and go into projectiles next time. I do have some more stuff that we got to cover with regards to vectors, but this gets us a good way along. So by all means, use what you already know plus what you've learned so far. And just remember, things pointing in the positive direction should have positive components, and components pointing in the negative direction should have negative components. But the magnitudes of vectors in this world are always positive. Okay. You guys are free to go. Don't forget to chat me your first and last name before you do. I will see you next time. Oh, and don't forget, the first test, the online test, is due this Sunday. You get, I think I made it where you get 3 attempts and I only count your highest. And you've got the practice test open the whole time. So make sure you get that done by Sunday at 11:59 p.m., just before midnight. Have a good one. I'll wait for the last person to leave in case anybody has any questions. Brianna, Charles, anybody have any questions? Ah, yeah. Make sure you chat that. How about Daniela or Holden?
I do.
Go for it, Daniela.
Um, so I missed two classes. I know that you said like you won't like really count it unless it's like we're not doing the work and everything like that.
Right.
But I think I mentioned to you before, I actually took a physics class and I dropped it like halfway through the semester. So
Mm-hmm.
like I understand right now.
No problem.
And with work, it's really hard. So, because like I get off at 5, and then by the time I get home after traffic, it's almost 6. So I didn't know because it said you have to join the class by 35.
Oh,
So,
gotcha.
yeah, so I haven't been joining,
Yeah.
but I just wanted to bring that up.
Okay, no problem. And
And
and if you do sign in that late, that's fine. I'm not. It's not like it's bothersome to us. Okay.
okay.
I
And
wouldn't
then,
necessarily count you as being there, but it doesn't matter at all whether I count you as being there because I actually treat my online classes like they're asynchronous, so students are
okay.
completely allowed to skip if need be. But
And
yeah.
then, um, for the labs, I know it's asynchronous, but I was really confused because kept seeing like a Zoom thing for labs on Tuesdays at
Mhm.
12 to 1, but it's supposed to be asynchronous. So I'm trying to make sure that I'm not missing labs, especially because I'm at work.
No, no. In fact, I recorded at that time because there's a chance that people might be taking lunch at noon. So I'm just
Hmm.
trying to fit it in where they could if they wanted to. So it's like
Okay,
another office hour. But again, that is completely officially asynchronous. So you're welcome to just watch that later. I'll
that's
put
what
it
I
on my
do.
YouTube channel.
Okay, and then I'm confused because I'm so sorry. There's so much.
No problem.
Um, because for the labs, I'm doing it on the lab like page, but then I'm seeing the same lab is due like the Monday at 9 a.m. So I'm submitting the same lab twice. Am I supposed to be doing that?
Oh no. Okay, so the lecture portion of my Canvas course,
Hmm.
occasionally assignments pop up there for lab. They're not supposed to be there at all. That just happens because when I copy it from another course, that other course had lab built into it, so it would throw it in there.
Okay.
You're looking at it before I've had time to throw the labs away.
Okay, so yeah, so today I did the same thing like I did last week, and I sent a message last week. I put it in the comments. I was like, this is the same lab, so I just submitted the same
No
thing.
problem. I'm not going to take off for it, and even if you keep doing it, it's not a big deal. The main thing is make sure you turn it in at the lab Canvas course, as
Hmm.
long as you've got it there. And by the way, I've been putting it at 9 a.m. Because I do that, and students won't necessarily look at it at that
Hmm.
time in the morning. I'm actually going to now start allowing it till 11:59 p.m. on Tuesdays.
Okay. And then one last thing. I am so sorry.
No problem. It's
I feel
fine.
like I'm bothering you. So I like again, I'm working and I'm juggling this class, and this is actually like I'm doing this on the side. I'm actually at ODU full time.
Mhm.
And I'm gonna be direct with you. I completely forgot that the homework was on that thing, and that's actually the same website I used when I was doing physics last semester.
Right.
And I was like, last week, I was like, where's my physics homework? He hasn't posted any homework. And then I like read through the syllabus again and I was like, oh crap. So I bought it right away, but I haven't turned in any of the homework for those weeks because I definitely forgot about it. Is there any way I could still turn them in?
Yes, in fact, I take off a limited number of points for it being late. I mean,
Okay.
it's more each day that it's late, but it gets to a point where it doesn't take off anymore.
Okay.
So turn those in, and if I happen to go across it and see that they're really, really late, even though they're not really supposed to necessarily that late, I'll probably give you some of the late credit back.
Okay. I'm
Okay,
gonna
and I do that
cuz
for
I
everybody.
okay, cuz obviously I have to keep up with like the ones that are posted too. So what I'm trying to do is do like week one while I'm doing my week three, week two while I'm doing my week four, so that I can still, I don't turn in anything else late, but I get those in as well. Because I am also doing chemistry too. I'm trying to get my prereqs for med school applications.
Right. Yeah.
And then I'm doing full time at ODU and working full time. So, and I made like a Google Sheets where I had all my class assignments, but I
Right.
didn't have yours at the time, so I didn't even upload it.
Gotcha.
But
Well,
okay.
the way this class works, you meet on Monday night, so you expect all your homework to be done by 11:59 p.m. on Sunday. What
Okay.
I would do is try to keep this deadline for the chapter 3 homework, which I think I've already put back a little further than this Sunday. Get
Okay.
that one in on time and be working on chapter 1 at the same time.
Mm-hmm.
Then when we start the next chapter, which would be chapter 4, I want you working on chapter 4 and knocking out chapter 2. Uh,
Okay.
I would rather you get those really late unless you learn that, oh crap, I can't do 3 because I don't understand 2. That sometimes happens, so that'll be
Yeah.
perfectly normal. But let me know when you get 1 and 2 finished so I can go back and check it.
Okay. And again, I've done this, like I've done up until like mid semester of this class. It just was not working to me for me at my last school. So
Right.
I had to at Wesleyan, so I had to drop it. And so but I did understand a lot of it. I did well
Good.
on my exam, surprisingly.
Good, no problem. Yeah, and don't worry about it. Just make sure you have the ability to text me if you really don't understand something. Sometimes it takes more than just a typed email or even a typed text. So if
Hmm.
it turns out to be something complicated for me to explain to you, I can just set up a call for you, you to call me or me to call you, and
Hmm.
I can help you better understand. But yeah, I don't want you being confused so much. So make sure you get these questions answered as soon as you can instead of, it's nice. I'm glad you're asking me in class, but you can ask well before that too. Okay.
Okay, thank you so much. Yes, I will have those done. I will have three done and one done probably by this weekend because I've been keeping up with all my other homeworks where I'm
Good
not
deal.
like, yeah, so I'll
And don't forget,
probably
you do
have
have
those done.
a test that's due this coming Sunday that's on chapters just 1 and 2.
Yes,
So
I am aware.
it's way more important to get that done than it is to do the homework. And doing the practice tests is every bit as good as the homework. So if you feel
Okay.
like just don't have the time to do the homework a little later. Just get those tests done.
Okay, yes, I've been going through my old physics notes to like help me with anything I forgot, but it's pretty much the same. Like I was just looking at it, and unit three for us were also vectors,
Right.
so we're like in sync.
Cool. Good deal.
Okay, thank you.
You're welcome. Have a good one, Daniela.
You too. Bye bye.
Bye bye. Charles, you have a question, sir?
Yeah, I did have one question. The um, the 14-day trial for the Pearson site.
Right.
After that was over, I paid for um the your class,
Right.
and I was wondering, is the textbook a different payment than just paying for the class?
Well, the last I spoke to any of the representatives from Pearson, they told me they were no longer selling just access to mastering, that it always came with the ebook. So what you bought should have given you access to the ebook. So when you go like in my Canvas page, you're going to
Mhm.
go to your course and then click on Pearson Access on the left-hand side. And one of those, once you get to go into Pearson, you should see something that says e-text on the left-hand side and click on that and that'll show you the text.
Okay, yeah, because I was in there earlier and I clicked on e-text and it said this doesn't come as part of your purchase, or you don't
Oh,
have an
crap.
access code or something.
Okay, so yeah, did you buy it from our student store or did you buy it from somewhere else?
I bought it from when I was going into it and it said you need to buy the subscription. I bought it from there.
Oh, really? So you went in through my Canvas course and purchased it from Pearson directly, and they
Yeah,
sold you one without the textbook?
I guess so.
Okay. Uh, it's probably going to be a different price. Do you recall how much you paid?
I think it was 84.
That sounds pretty close to the price. I will check with my representative. It might be something where you have to pay a little bit extra to get the book with it. But yeah, if you don't have the book, you're going to be kind of in a bad spot. If you really need to
Yeah.
save the money, uh, you could buy an older edition, like a third or a second edition, just to have access to it. but I'm surprised they're letting you have any access to the mastering site without it. Uh,
They might have also sent me an access code in my email, and I have to dig for it. I'll have to look. And
okay.
yeah,
Yeah, find that out, and if you can't get anything done, let me know, and I'll talk to my sales rep, and they usually can work something out to get you finished up.
okay. Yeah, and then the other thing, she mentioned it before. So our labs, we're supposed to be submitting them in the L02B course.
Your labs, yes, yes, in the
Okay.
L02B course.
Okay, cool. Thank you.
No problem. Have a good one, Charles. Good luck.
All right, you too.
Bye bye.
Bye.
All right, I guess that's it. See ya.